Okay, so today I am going to go over Mod 10.1, and we are going to go over the inverses of quadratics and cubics. So as you'll notice, I don't have the book pulled up. We are not going to use the actual HMH book. Instead, you're going to be taking these notes on a separate sheet of paper. So if you haven't already gotten out a separate sheet of paper, go ahead and do so, and then title it Mod 10.1, Inverses of Quadratics and Cubics. So the first thing is we're going to look at a quadratic, and we're going to look at y equals x squared. Okay, the parent function. So the first thing is, what is the inverse of the quadratic? So if you recall, when we find inverses, we switch x and y. And then step 2 is to solve for y. So if I do that here, I would write x here and y here. And then since I'm solving for y, I'm going to take the square root of x, and I'm going to get that the square root of x equals y. And another way that we can write this is that the inverse function is equal to the square root of x. So what we have is that x squared and the square root of x are inverses. And we kind of already knew that because that's why we take the square root here when we're solving for y, or like when we had questions back in, what was it, like module 4, when we would have like x squared minus 4 equals 0, and we would solve. We would add 4 because that's the inverse of subtraction. We would have x squared equals 4, and then we would take the square root in order to get rid of the square, and we would get our plus or minus 2. Right, so we kind of already knew what the inverse was, but one thing I want to point out is that when we graph these, so the graph of x squared looks like this. And now if we're switching all of our x and y points, if you think about this as a t-chart, we would have the point -1, 1, the point 0, 0, and the point 1, 1. So if I was doing the inverse, y equals the square root of x, that t-chart, if I switch my x and y, it would be 1, -1, 0, 0, and 1, 1. So graphically, that's 1, -1, 0, 0, and 1, 1. And so it looks like this. And then if you guys remember back to Algebra 1, we learned the vertical line test. So if you can draw a vertical line and it hits at more than one point, then you know it's not a function. So the inverse written like this is not a function. So what we often do is we often restrict the range so that y is greater than 0. So what that means is that this part below here that is below 0 is not included. So we only include these y values that are greater than 0. So when we talk about the inverse of a quadratic, because we're looking for the inverse function, we have to include that the range is only greater than 0 so that it remains a function. So now it passes this vertical line test, right, in all spots. So it's now a function. Now, we won't be required to graph these in today's work, but I did want to draw your attention to that. All right, and then the next one, so we've talked about quadratics. Now we need to talk about cubics. So if I have y equals x cubed, and I'm finding the inverse, I'm going to switch x and y. I'm going to solve for y now by taking the cube root, and I get the cube root of x equals y. So I can write the inverse function is this. So now, if you remember what we just did with our quadratics, let's first graph what y equals x cubed looks like. And I'm going to use a t-chart. And just because we're a little bit less familiar with this one, I'm going to choose not just 3 points, sorry, 5 points. And I'm going to plug these in. So -2 cubed is -2 times -2 times -2. So that's -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. So my function for this is going to look, let me start over there, something like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Alright, so my points are -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. So it looks kind of like a little S. And if I am looking at the inverse function, which we said was y equals the cube root of x, our t-chart, just like when we're solving, you just switch your x and y. So -8, -1, 0, 1, and 8. And -2, -1, 0, 1, and 2. So let's see what the graph looks like, and let's see if we're going to have to restrict our domain or range like we had to for the quadratic. So I have the point -8, 1, 2, 3, 4, 5, 6, 7, 8, -2, -1, -1, 0, 0, 1, 1, and 8, 1, 2, 3, 4, 5, 6, 7, 8, 8, 2. So if I draw this, here's what I'm looking at. And it doesn't actually look like we need to restrict it, because if we look, our vertical line test, no matter where I draw this, is going to pass. So it is a function without a restricted domain or range. So quick little recap is y equals x squared. The inverse function is the square root of x, and where y is greater than or equal to 0. Okay, and then for y equals x cubed, our inverse function is the cube root of x, and we don't need any restriction on our domain or range. So now we are going to do some examples. And so this first one, it says find the inverse function. So again, remember this is just y. So if I'm doing the inverse function, I just switch my x and y. And then I solve for y. So I'm going to add 3 to both sides and get x plus 3 equals 2y cubed. Divide by 2. And I get x plus 3 over 2 equals y cubed. So I'm going to take the cube root in order to get rid of the cube. And so my cube root and my cube cancel each other out, and I get that my inverse function, let me fix that, my inverse function is the cube root of x plus 3 over 2. For number 2, same thing. This is y. So I'm going to switch my x and y and solve for y. So in order to get rid of the square, I have to take the square root, and I get the square root of x equals y minus 2. Add 2 to both sides, and I get the square root of x plus 2 equals y, or that's my inverse function. And there we go. Okay, for numbers 3 and 4, remember to get rid of the cube root, you would cube both sides. So once you switch your x and y, make sure you do that. The last thing I want to show you is when it says to state if the given functions are inverses. You're going to have to recall back when we did inverses that if f of g of x equals x and g of f of x equals x, then f and g are inverses. So we have to check this. So what this is saying is plug function g into function f. So I'm going to do that here. Here's function f. I have n plus 2 squared. There's function f. And instead of writing n, I'm plugging in the function g. So I'm plugging in the square root of n plus, the square root of n minus 2. And so we see that the negative 2 and the 2 cancel each other out, and I get the square root of n squared. And again, the square root and the square cancel, and so I get n. So did I get just x or just n in this case? Yes. If I was doing g of f of x, I would start with function g, which is the square root of n minus 2. And remember, instead of plugging in n, I'm plugging in the function f. So the function f is n plus 2 squared. So the square root and the square cancel, and I get n plus 2 minus 2, and these cancel, and I'm left with just n. So since this statement is true and this statement is true, then f and g are inverses. So that's what I would write, was since f of g of x equals x and g of f of x equals x, f of x and g of x are inverses. And I guess maybe what we should have done here is instead of using these x's, I guess we technically are talking about f and g of n, right? So let's go ahead and use n's instead. But they're just variables, so that's arbitrary. So there we go. And that's what you're going to do for all of these. So you just have to test if this statement is true for each one of these. So check if f of g of x equals x. So starting with function f, x plus 2 over 2. But I'm not plugging in x, I'm plugging in the whole function g, which is this. 2x cubed minus 2. And I made a little typo here, I forgot to put the cube part there. So looking at this, I have that negative 2 and that positive 2 cancel. That 2 and that 2 cancel, and I'm left with the cube root of x cubed. And those are inverses. So it's true for this one. Don't forget to check it for g of f of x. Good luck, guys.